Welcome to my talk. So, first of all, I want to say that it was a pleasure for me to organize and invite you to this workshop organized with Jean-Paul. And I think one more time we can cheer Jean-Paul for the enthusiasm he has invested in the organization of these 2 days. The energy you spend for the organization is has been done, well done. Well, so my presentation is titled From Biomechanics to Robotics. So I will try to explain you how biomechanics can be used to extract some dynamical parameters of humans, invariants of motions, which could help us here in GPTO to simulate and then generate motion of anthropomorphic system. So, in fact, because of the redundancy of the musculo-skeletal system, because of the mechanical behavior of the musculo-skeletal system, and particularly muscles, you can see on this video that there is a lot of way to do a given motion, here climbing stairs. While when we simulate and then generate the motion, it's a little bit different. Little bit less dynamic, perhaps. But you can see it's complex motion, and we here control the dynamic of the movement, which is a very complex problem. So, in fact, here at GPTO, we hypothesize that a better understanding of the mechanical behavior of humans could lead to better simulate and then generate human-like motion. And at the opposite, we assume that if we succeed in generating human-like movements, that we shall have better understood the motor control in humans. So, the problem of simulating and generating human motion is very complex because, as I previously mentioned, the redundancy of the musculoskeletal system, in fact, the body involves more than 200 bones and 200 degrees of freedom at kinematic level, more than 600 muscles. So the brain, for a given motion, has to first select one trajectory, and on this trajectory has to select the muscle which will do the movement. So, simulate and generate need a model and an anthropomorphic system close to humans. If not, you will have very different behavior. But of course, our anthropomorphic systems are not close to humans. While there is huge similarity, there is also huge differences. One principle is that, of course, robots are rigid, while humans are flexible. Humans have muscles, while robots here have electrical motors. And muscles have very good properties to dissipate the energy by the way of the eccentric mode, which is very helpful for human. Very difficult to do with electrical motors. But there is also similarities. For example, if we compare HRP2 and humans, maximum torque at the knee is around 200 Newton meters, quite similar. The maximal peak power at the upper limbs, lower limbs, lower limbs, twice than in humans for HRP2, while some parameters are very different. For example, maximum rotation angles at lower limbs around 1,500 for humans, only 300 per second for HRP2. So, of course, it's very complex to generate human-like motion with an anthropomorphic system, which is different in its conception. So, a little bit of literature now, and some people here are in the conference room, so you can discuss later with them if necessary. So, to simulate and then generate motion, many authors in the last 40 years propose to answer this open problem, propose to use optimal control, motor primitives, I will detail later, or the abundance of the musculo-skeletal system, which could be helpful to generate given motion. So, first, optimal control. In accordance with the theory of evolution, hypothesize that for a given motion, humans tend to minimize a cost function. Minimizing a cost function allows us to predict muscular forces, joint torque, or segment kinematics. Of course, these variables, these parameters, are not exclusive between them. But the question of optimal control faces a major question. It's unrealistic to imagine that we can minimize a parameter which is not perceived by the central nervous system. So the question is, what is perceived by the central nervous system? What is taken into account? And then, what is minimized? We can't minimize a non-perceived parameter. So, of course, the cost which could be minimized in a given motion is multiple and depend to the task to be achieved. Of course, if you are doing a whole body motion, if you are doing an accurate movement, if you are reaching, pointing, you won't minimize the same cost function. So, during the last 40 years, a lot of authors proposed different cost functions which could be minimized in humans. So, some authors propose, as the kinematics of the segment is well perceived, authors propose that the jerk, which is a derivative of the angular of the acceleration, could be minimized in some basic movement like pointing task or reaching an object. Muscular forces are also well evaluated by the central nervous system. It was shown using the Borg scale, which is highly correlated with the activity of muscles in human. And it allows some authors to propose that human minimize torque at the joints or the torque change, which is a derivative of the torque developed at each joint. Kinetics, characteristic of the segment, are also well perceived, and some authors proposed that we minimize the kinetic energy, or logically, some others propose that we minimize the energy consumption, and so it's the minimization of the metabolic expenditure, which could be minimized. The optimal control, I will explain why later, is not optimal for wall movement. It can't explain wall observations. So in the last 15 years, other authors suggest that we have motor primitive theory, and the motion so is in these theories encoded. The humans encode a set of motor function, and the authors propose that at different level. So it could exist kinematic primitives, or muscular synergies, or neuronal primitives. So I will explain briefly these three elements. So kinematic primitives, the kinematic primitives explain, well, so in a given motion there is a fixed proportion of the movement which is done by each joint. So we freeze some degrees of freedom by acting simultaneously different joints with a fixed proportion. Some author explained that it could explain why we always observed speed profile as Gaussian profile, or other propose that it ensures the reflex in activity in humans. Others propose that there is muscular synergy, which corresponds to the co-activation of different muscles, which also frees some degrees of freedom at muscular level. And particularly, it's interesting to explain co-activation as a joint which is always observed, but never optimal. Another theory, in a different manner, Scholz and Schoner in 1999 propose to explain the variation observed between the subject and propose a new theory named uncontrolled manifold. There is only some degrees of freedom which is controlled by the brain, and Latache and collaborator recently suggest that it's very benefit for humans because it's very helpful. They have only some degrees of freedom to control, and the others could vary from one movement to from one motion to. You can modify so the motion at each task. And because our colleagues are the problem of this theory is that there is it's not a closed loop theory, so there is no feedback with optimal control or synergy when controlling a motion. So other authors propose that we used an optimal feedback control, which could also explain the co-activation of muscle at the joint, which involve agonist and antagonist muscle. Well, so now I will show. So of course all these theories are not exclusive between them, and we could correlate some elements of these theories. Well, but to extract, now I will do a little lecture of biomechanics, classical one, and I will explain how biomechanicists can how they study the mechanical dynamical parameters in humans and how they can extract invariants, muscular synergy, and I will show some basic results. So, okay, well, so to realize biomechanic experiments, we classically there is pointing like that? No? Okay. We classically use optical motion system here. Force platform to measure external forces applied on the subject, and here we have also handlebar equipped with a 6-cell sensor in order to determine the reaction forces applied on the preparation phase EC and during the landing, so we use the force platform. The subject is also equipped with a wireless sensor which allows us to determine the muscular activity. So the goal here in Gepetto is to simulate and then generate whole body motion and dynamic one, as you can see here. And I will later. So here reconstruction of the three-dimensional kinematic of humans after using and merging external forces and kinematics and anthropometric data. We, by the way of inverse kinematics and then inverse dynamics, we can compute the torques applied as jet joint or at different level muscular forces. Then, if our setup involves enough subject, we can temps passe vite le matin. Et if the experimental setup involves enough subject, we could, by the way of statistics, extract invariance between subject. Then, if we use an accurate model, we could simulate or generate the motion using the invariance of motion extracted here. So I will briefly present you two examples. For example, in when cycling, and when the power increase here at the crank, we always observe a spontaneous sit-to-stand transition. The reason of this transition remain unclear, and we don't know what is minimized or what the reason why we transit from one position to the other. So here I show you the experimental setup, a classic one involving 47 here reflective markers on the subject, and we measure at the pedal, the seat, and the handlebar, the external forces applied by the subject, which allow us with a classic bottom-up inverse dynamic computation to determine the joint at the hip, the torque at the hip, the knee, and the ankle. So here it's a polar representation of the crank, and we can see the variation of the torque here at the hip, the knee, or the ankle. Here it's a maximal power, and we can see, for example, a maximal torque at the knee of around 200 Newton meters. And using clipped pedals, when the foot raises, we can see that we are going from extension to flexion to raise the foot. Well, so using inverse optimal control and the previous literature, we compute a moment cost function here, which is a sum of the square of the torque at the hip, the knee, and the ankle on one cycle, on one revolution, and on both left and right lower limbs. And we can see that the torque increase in the seated position when the power increase, and in the standing position also the cost function increase. But the rate of increasing is higher in the seated position, and the both lines crossed around the spontaneous sit-to-stand transition. So it's parameter who could explain the transition. Subjects tend to minimize the torque developed at the lower limb. I apologize because it's an old figure. Now we have a wireless system without the cables. It's easy to construct the experimental setup. So to extract also muscular synergy, we need to measure the activity of subcutaneous muscles using electromyographic study. So here in this experience we have measured the activity of 9 muscles. We can see here, for example, how it's always a polar representation of the muscular activity of 2 muscles, the rectus femoris and the biceps femoris. Concentric circle are the increase of the power, and the red one is the spontaneous transition from the seated to the standing position. And we can see that, for example, here the rectus femoris, the time of activity of the muscle increase when in a standing position. It's the same for 8 of the 9 muscles observed here. Only the biceps femoris have a decrease of activity. Well, this cycling experiment allow us to extract 4 synergies, one composed with one involving rectus femoris and tibialis anterior, one of extensor and one of flexor. And we can see here when each synergy is activated along the cycle. I apologize, I have to go. Well, so now here at GP2 we continue to analyze high dynamic motion. We are now studying parkour, which is a new activity developed in France in the 90s, while we can find on the website that it's not in the 90s who was created this activity. Here it's a video coming from the 1930. So this activity he survived, I think. This activity leads to avoid obstacle of the environment to do a locomotion. So nowadays, parkour, it's that. So it's very high dynamic motion, and it seems to be very free, while there is a very similar exercise which is done by these practitioners. For example, the precision landing. We could extract precision landing from practitioners. Here nothing. And I tried without success. I tried without success to land with HRP2, but my colleagues don't want. But after searching on the site, I just find one robot which can land here. You can see eccentric mode, which is important when landing, of course. Well, so briefly some results. We can see that we compare practitioners and non-practitioners, and we can see on this result that, of course, practitioners prevent injury by extending the time of landing. Here is the time of landing of practitioners, and here the time of landing of non-practitioners. And we can see that the practitioners land smoothly, while the non-practitioners are very straight. And of course, as the energy to be dissipated is the same and correspond to the potential energy of the land, if you have less time to dissipate the energy, so you need to generate higher torques at the lower limbs. So that's what we can see here. The torques in non-practitioner is higher than in practitioners. Well, so now I speak a lot about biomechanics and how to determine invariants and internal dynamic internal parameters. Now I want to I apologize. I want to show you the first result of simulation. So I want to thank Gallo Maldonado, which is in the conference room here. It's a PhD student which work on the simulation of the whole body motion, and we can see here results on the left coming from inverse kinematic, which allow us to determine the real motion of the body and of the different segments, and here on the right our first simulation of a whole body motion. So it's a very recent work, so we can discuss further about the simulation later or during these 2 days. We have a little problem at the beginning of the flight phase because of angular momentum, which is not correctly determined. Well, and of course I can speak about generation of the motion. Here in Gepetto, we have strong know-how and algorithms are based on mockup, retargeting, optimization. Now I can show you and finish my presentation. By showing you the know-how of Gepetto in generating motion, but of course we will discuss during these 2 days about this motion.
Thank you, Bruno.
Thank you. Very
No, sorry to stress, but I would like to have time for a few questions, and if you start drifting the time, okay, you know that.
Of course, I apologize. I'm not the center of this workshop.
Okay, but we have time, of course, for a few comments or questions.
And I just want to show you, coming from a museum here in Toulouse named Paul Dupuis, a very beautiful motion generation. And now you can ask a question.
Okay, then some
comment. There are a set of automaton which generate human motion. I think it's very beautiful. So if you have time and see some people
L'œuvre qui est
are
derrière moi
staying
a
in
été
Toulouse
faite
this
par
weekend, it's very, very interesting to see this motion generation. Very interesting. Well, no question.
Then just yeah, okay, Olivier. We have only one microphone. Who is in charge of the microphone? Justin? No, but it could be.
Hi, Bruno. Thank you very much for the nice presentation. Regarding your last results with the skeleton jumping, actually, what were the tasks that you were trying to control to generate the motion with the skeleton?
We divide the activity in 4 phases. Yeah, we divide the sequence in 4 phases: preparation of the jump, then propulsion, flight, and landing. And in each phase, we minimize a different cost function. During the propulsion, we tend to minimize, for example, angular momentum. During the initiation, we are trying to control the posture of the subject, minimizing the final position, the position and the final position. But I will explain perhaps more details later what we minimize in each. So we divided the motion in 4 phases. We minimize different cost functions.
Okay, one more, Frank. Okay. Go ahead.
I don't know, and we try to extract what is the task we try to achieve when we land, and it's a very complex question. What are we trying to do? I think first we try to stabilize, but stabilize, there is a lot of ways to stabilize, and I don't show you, but there is different sort of landing. There is also roll landing for parkour practitioners, which is another way to stabilize the motion, so they are rolling on the back at the initial contact. So depending, in fact, it's a very complex question, and we can discuss, but for each motion, I think I said that the costs are multiples and depend on the task to be achieved, of course. And if you are landing and if you are reaching, pointing, it's a different cost function which is minimized, yes.
Okay, then thank you again, Bruno, and sorry again for stressing you. Okay, then